All right, guys, so we're going to start talking about, or we're going to continue on topic 2 where we left off. The last thing we talked about in the previous video was the modulus of elasticity for steel. And just as a little recap, modulus, oh, this is a really tiny highlighter. Let me fix that. Modulus of elasticity, that is basically the slope of the elastic region. Okay, so moving on here, we're going to talk about a couple of more kind of elements to the stress strain diagram before we do an example. But we have something called strain hardening that happens when we apply load to a material. So I have an example here, and it's imagine bending a wire that is ductile. So a wire that has flexibility to move when you bend it, okay? And let's say you bend it so much that it goes into the plastic region, okay? And now when we're talking, or when I'm using words like plastic region, you should be familiar with, oh, plastic region means that there is going to be some permanent deformation. Meaning if I remove that bending, if I remove the load causing that bending, the object will not bounce back to its original shape anymore. There will be some permanent deformation, okay? So again, I guess this is what I'm talking about. What if we now remove the load? So whatever elastic strain, so whatever was the strain from the elastic region, that part will go into the recovery of the material to go back to its original shape. And whatever the plastic portion is the part that will result in some permanent deformation, okay? We call this permanent set. So it's a certain amount. I'm going to draw it here. I think I've drawn this a couple times before, but basically this is my original member, or I mean, we used a wire here, but it can be anything. And I am pulling on both ends. Actually, let's say this is fixed and we're pulling on one end. This is a little easier to understand. Let's say this is fixed and we're pulling on one end. What happens is, right, if this is elastic, if I'm only pulling with some force P to get this into the elastic region, it'll be pulled out, right? But when I remove the load, I have the same shape that I started with. So I'm able to kind of pull with a load, remove the load, and I get back to the original length. But plastic deformation, so I can have the same system, same bar, and I pull on that bar with, let's say, a force of 10p, which means I'm going to cause this to basically deform a lot more. Part of that deformation is deformation in the elastic region. Right? And only part of it is plastic deformation. So when I go back, when I remove the load now, what did I put here? Now when I go to remove the load, what happens is I have a permanent set. So you can see here, this was my initial length, and I have some permanent set here because only the elastic part recovered. Okay, so you might be wondering, well, what does this have to do with strain hardening? What is strain hardening? Strain hardening describes basically these interatomic forces that we have to overcome to elongate the specimen elastically. Okay, so you have to think of it like this. It's almost like this internal resistance of the member. I'm pulling with a force P, but the member doesn't want to move. It's going to resist that force. And it's all these interatomic forces of the system in terms of the material are resisting my tensile force trying to elongate it and trying to pull it into the elastic region. Okay, and basically what happens is the same forces when I remove when I remove the load, those same forces, those interatomic forces, are the ones that are pulling all the atoms back together to put it back into the same shape that it used to be in. Okay, this is a equal and opposite reaction. Okay, so again, what we know is the modulus of elasticity stays the same. The slope is the same for this kind of addition of load and the removal of load. Let me see if I have a picture of it here, so I'll get to that picture in a second. Okay, actually, let's get to it now. What I'm trying to say is this. This is me applying some force P on the system like I drew before, right? Some force P, linear response, elastic region, all is good. I remove it. We go back to the same shape. Nothing changes. Now, let's say again here, this is my other part where I apply a force of 10P and I remove it right at this point A prime. What happens is we call this unloading. Unloading. And I have this unloading line that acts at the same slope as my loading line. Okay? And I now have a new stress strain diagram. My new stress strain diagram starts at this point. We call it O prime or origin prime, something like this, right? And I get to start all over. I get to now load the specimen. This is unloading, but I'm going to now load the specimen. Loading. And now this is all the elastic portion. And what happens is I now have a higher yield point that this is going to experience because of something. So basically, I'm going to put increased. And this is called strain hardening. So we're almost kind of slowly priming and prepping our member to be able to resist a higher amount of load, okay? And this is basically, the one thing to know about this is now what we've done though, we do have a smaller elastic region. This is important. We are decreasing the elastic region in our new curve. So this is our new curve. We're decreasing the elastic region. So our material is less ductile. What does that mean? We don't get as much of a notice when it's going to break anymore because we're kind of already slowly pulling it to that point of deformation. Instead of a quick pull, it's now a slow pull. But then when we're going to try to load it heavily, it's going to break without as much of a warning. It's not as ductile as a material anymore, okay? So what happens here, strain hardening can be very useful to increase the strength of a member, okay? So we do have pre-stressed material, which means that we do apply some type of stress to this material so that we can increase the yield, and we do build a lot with those materials. But you just need to be careful because we don't want to pre-stress it to the point where this material goes from being a highly ductile material to something that gives you no warning before it fails and completely alters the stress strain diagram that we choose to use for ductile materials, okay? The next thing, I just kind of put those notes here. So these are some notes you guys can copy down. Okay, the next item is strain energy, okay? And strain energy, basically, when we have a material that's deformed by some external load, like the one I had just drawn, the bar being pulled from a fixed support, the external work is going to be stored inside of the material as internal energy. So we have external energy is equal to internal energy, right? This is conservation of energy, okay? We call this internal energy strain energy, okay? And the reason we call it that is because it's related to basically the strain inside of the material that happens due to the load. And you can think of this as just like work. So if you guys have taken dynamics, or if you haven't taken dynamics and you've taken physics, you remember that basically whatever work I do on a system translates to some type of internal work on the system. And that's really what this class is about, actually. We want to know what those internal reactions are, those internal stresses and strain, and what's happening inside of our member. Because if we understand what's happening inside of our member, it's going to tell us a lot about how it behaves on the outside eventually. So we cannot see the internal forces pulling apart or affecting the member, but we're going to see when a member fails, right? We want to know before the failure happens what's happening inside the member so that we can prevent those types of things, okay? So basically we have the strain energy and it's just the internal work here, okay? So let's talk a little bit more about strain energy. And let's suppose, let me see how many slides I have for this. Okay. Let's suppose I have this 3D block. Okay. And I have, again, my normal stress, sigma. this is 3D, you can kind of see this as a face. We'll say this is the delta Z, this here is delta Y, and this is delta X, okay? We call this uniaxial stress, this sigma. So sigma uniaxial stress, it acts on one axis. It's normal stress, okay? And then this stress develops a force. So stress okay? So we have delta F equals sigma delta A. We know this, stress is equal to F over A. And we can say that this is really just sigma times delta X delta Y. That's a cross-sectional area. And this is on the top and bottom faces of the element after the element undergoes some vertical displacement, right, from this load. Okay, and what happens here is this force increases uniformly from 0 to some final magnitude. We'll call it delta F when the displacement epsilon delta Z occurs. Okay, and basically then we can say our average force is equal to delta F over 2. Okay, this is our average. And now we have delta V, which is, this is our internal is equal to internal. That's what we're going to do here. So this is the work is equal to 1/2, that 1 over 2 delta F, epsilon delta Z. We're plugging everything in. And now we can say this is really just sigma delta X delta Y epsilon delta Z. And we know that delta V is equal to delta X delta Y delta Z. Sorry, this is delta U, internal energy. This is delta V. I don't want to, let me see how I can write this so it looks more like a U. Delta U, there we go. Okay, and now we can say that delta U is just 1/2 epsilon, sigma epsilon delta V, change in volume, okay? And we're gonna get to some final equation here. So we call this U, which is delta U over delta V, as 1/2 sigma epsilon, and this U, I'm going to define this. This is the strain energy density. Of a material, okay? For any material, so in this class, we're always dealing with linear elastic material. So any material that is in the linear elastic portion, actually we're not always dealing with linear elastic material. We will deal with material that pushes to the plastic region, but for most cases we're dealing with material in the linear elastic range. Whenever we're dealing with material in the plastic range, we'll be given the stress strain diagram or information that we can use. But otherwise, if we know that it's only being pushed to the linear elastic range, we can apply Hooke's law, which is stress is equal to the modulus of elasticity times strain. And basically, we have this formula for strain energy density. And we call this, because this is elastic strain energy density. So another property that's important for these stress strain diagrams. Okay. So let's move along here. Okay. One more very important factor to talk about is the modulus of resilience. And I kind of put all the information on this slide for you already. So basically here, this is our modulus of resilience, or U, and it is a function of our sigma and E. And all you'd have to do to get this modulus of resilience is take the area under the stress strain diagram. Okay. Okay, the other modulus we have is modulus of toughness. So this is the maximum amount of strain energy. So you're going to take the area under the curve or the integral all the way up to this failure point. So of the entire diagram. This is only the elastic portion. It's the integral for elastic. This is the integral of the entire region. Okay? All right. So here is the summary from the book. It kind of gives you all of this information. I know that this was a lot of heavy, like, new terms and memorizing. They are really important to know, and we're probably going to have a little in-class quiz about it. So it's best if you do study and do understand all of these different terms, and that you do know how to use the stress strain diagram, because we will need that to solve certain problems. Okay, so that is super important. Make sure you're really familiar with all of the terms, and especially familiar with this. All of these terms, no, not this, whoops, from the previous video, where is it? Bear with me. This thing. Make sure you're very, very familiar with this slide. Okay, on my PowerPoint, it's slide 4. Okay, it's the one we went over yesterday. All right, so let's do example 1. Okay, we can see how we apply these concepts now. Okay, so the stress strain diagram for an aluminum alloy that is used for making aircraft parts is shown. If a specimen of this material is stressed to 600 MPa, I like to highlight important info. Determine we want permanent strain if this when the load is released. Also find the modulus of resilience both before and after load. So we want okay. So one thing before we kind of jump into solving this problem, we know that the specimen is stressed to 600. So we can clearly see that this here is the elastic portion. My yield is 450. I'm stressing it to 600, which means that I definitely have permanent strain. If this question said it is stressed to 300, what would be the permanent strain? 0, because we're still in the elastic region. It's like a freebie question. Okay, but it doesn't. It says we go to 600. Since we now are in the plastic region, we know that we have some permanent deformation there. Okay, the first thing we can do is we can see that at 600, it's already telling us, but you know, in test problems or other problems it might not tell us, so we have to kind of guesstimate here. It's telling us that at 600 we have a strain value of 0.023 millimeters per millimeter. Okay. Now what happens is, again, when the load is released at that point, we know, because I kind of just talked about this, we know that this releases along a line that has the same slope as this line. So this line has a slope of E. Well, guess what? This line also has a slope of E. Okay, so I'll write that here. Line OA is parallel to line CB. Okay, which means that we can easily solve for the slope because we can use the yield point, 450 MPa divided by 0.006 millimeters per millimeter. And that's equal to 75 times 10 to the 9, so I'm going to put it in gigapascals. Okay, now we can see, again, that this E value also has to equal this line BD over CD, because this is just rise over run, right? So I can say now, okay, well, I know E is 75 times 10 to the 9 pascals, and that has to be equal to 600 times 10 to the 6 pascals divided by that distance CD, however much I had moved, right? So I can now get CD, which is 0.008 millimeters per millimeter. And that's here basically from here to here. Okay, and what does this represent? This represents amount of recovered elastic strain. Okay, but we want to know what the permanent strain is. So let's continue. How do we find the permanent strain? Well, we're really looking for this epsilon OC. How much, basically where the new line starts at. This is the permanent strain. How much did not recover? Okay, EOC, epsilon OC. So all we have to do is take the 0.0023 and subtract the 0.008, and we're left with 0.015 millimeters per millimeter. Okay, so our first answer. Okay, now what else do we want here? We want modulus of resilience. So we're going to say you are, let's do the initial one first, ask for both. And we can just plug in directly. The plastic limit, epsilon PL, and we have 1/2. We're going to use yield always for this, times epsilon at yield, and we get 1.35 joules per meters cubed. And you are final, because we have a new curve now, or a new line I should say. We're going to plug in the new limit, which is 600, and we know that that's at 0.008, and we get 2.4. So you see how this modulus of resilience has now increased from strain hardening. Okay, so that's something that you can note. UR increases due to strain hardening. Okay, makes sense because the area under the curve changes, right? Alrighty, let's see, we'll do one more problem here, and then we'll save the last two. Or we'll see. Maybe we'll do all of them and then talk about them in class. But for now, okay. So an aluminum rod shown here has a circular cross-section and is subject to an axial load of 10 kilonewtons that is shown. And we want to determine the approximate elongation of the rod when the load is applied. Okay. Okay. So the first thing we know is if we want to get the elongation, we need to know the strain, right? Because strain is what's going to tell us basically our delta over L, the change over L, right? So what we can do is to get strain, to get the appropriate strain, we can kind of back calculate and get stress first, okay? So let's see what we do know about this. We know that the stress AB is equal to some force over area. And we also have BC to consider because those have two different cross-sectional areas, right? So we have to calculate these both separately. So for AB, we have 10, I'm going to put this in newtons, divided by the cross-sectional area there. So we have pi times 0.01 squared, and we get 31.38 megapascals. And here again, we have 10 times 10 cubed newtons divided by pi times 0.075 squared, and we get 56.59 megapascals. Okay, so now what we need to do is we need to check what kind of deformation, what kind of deformation each of these sections experiences. So let's go to our diagram and look at 31.38 MPa. 31.38, let's just say it's somewhere here, right? That's in the elastic region. So here, okay, 56.59, oh, clearly that is, well, it's showing us, that's plastic. It's past the linear portion. That means that here I will have no permanent deformation, and here I will have yes permanent deformation. That's after the load is removed. Okay. Okay, so, but actually right now we're looking at the deformation when the load is on there. So they're both going to contribute. That's just something to note. Okay, another thing to note is that for AB, since it's elastic, we can actually just use Hooke's law. Right? So we can say that epsilon AB is just equal to sigma AB divided by E of aluminum. And all we have to do is plug things in here. So 31.83 times 10 to the 6 pascals, that's the number we got, divided by 70 times 10 to the 9 pascals, and we get 0.0004547 millimeters per millimeter. Okay, we can't use Hooke's law for portion BC because it's plastic. Okay, so we need to use the diagram. I'll put a note here. BC is plastic. This is super important. We cannot use Hooke's law because it's now a curve. Right? So what we have to do is use the diagram. So we go to the diagram and we want to see at 56.59, we're at 0.0045. And we can now say that delta is equal to the sum of strain times our lengths, right? So we have the 0.0004547 times that 600 millimeters, and then plus the 0.0450 times 400 millimeters, right? This equation is the same as the one I had just written. Okay. And we get a total of 18.3 millimeters. Okay. Okay. Now, next thing we'll talk about is Poisson's ratio. So basically, what happens here is we kind of talked about this, how when you apply compression or tension to something that's like a bar, so when you're axially loading it, what happens is the interior portion here, the center, gets thinner and the outside gets kind of fatter. So we have this ratio that we can actually use for another equation when we don't know all of our information, and we call this Poisson's ratio. So this is new, and we call this fancy little v Poisson's ratio. Did I spell that? No. Poisson's ratio. Okay. And the negative sign is in there because as we elongate the member, as the length of the member gets longer, this contraction, this part gets shorter, right? The cross section gets smaller. And that's why we have this negative, because it's inversely proportional. Okay. So let's try another example where we have to deal with Poisson's ratio to help us kind of solve what's going on. Okay, so we have a bar of A36 steel and the dimensions are given, and we have an axial force of 80 kilonewtons applied to the bar, and we want to know the change in length and the change in dimensions of its cross section after we apply the load, and we know, because they're telling us, that the material behaves elastically. Okay, the first thing we can do here, we can find the normal stress in the bar. And we can take sigma z, force divided by area, and they're telling us that it's 80, so I'm going to put this in newtons, divided by 0.1 times 0.05, the cross section, and we get 16 times 10 to the 6 pascals. Okay, now you'll have to get Poisson's ratio from the table in your book, okay, but I'll just give it to you. I won't make you ever find that. So for A36 steel, we know that Poisson's rate, well, actually, they're not giving us E either. They're giving us, I'll tell you what the E is. It's 200 gigapascals. okay? And Poisson's ratio is 0.32. So these are provided from table in book, or you can Google them. You just have to put in A36 steel. So basically they're given. I will give them to you. Okay. Now we can say that epsilon is equal to sigma over modulus of elasticity. That's equal to 16 times 10 to the 6 divided by 200 times 10 to the 9. And that's equal to 80 times 10 to the negative 6 millimeters. Not that weird symbol. Millimeters divided by millimeters. Okay, now we can talk about the axial elongation. So we have a strain in the x direction, which is equal to strain in the y direction, which is equal to negative nu st from steel, epsilon z, and we basically get negative 0.32 times 80 times 10 to the negative 6, and we get negative 25.6 micrometers per meter. Okay, you can leave this in whatever units you want though. Now what we really want is the changes in dimension. So change in cross-section we can calculate from delta x equals epsilon x Lx negative 25.6 times 10 to the negative 6 times that initial dimension, and we get negative 2.56 micrometers. And delta y is epsilon y, initial length of y, and we get negative 25 times 10 to the negative 6 times 0.05, and we get negative 1.28 micrometers. So really, this is just a lot of plugging in to equations after you solve. Okay, let's continue here. So we also have, we also have the shear stress strain diagram, which we haven't talked about yet. Okay, so far we've been talking about the normal stress strain diagram. And what happens here is we now, instead of distorting an element in terms of the length of the member, like by pulling or by pushing on it, we're distorting it by rotating it through some angle, okay? We're basically rotating it through some angle. So we have a shear stress strain diagram that looks something like this, and it's very similar to our normal stress strain diagram. And this is for ductile material, and you'll see some similarities here. So we have the shear stress tau is equal to G gamma, and this is for the elastic region, okay? You can think of G as similar to your modulus of elasticity, but we call this now the shear modulus, and we have a function that connects it to E and Poisson's ratio, okay? So the best way, because we already went through all these these definitions, and it's pretty much the same, the best way we can kind of get this is by going over another example. So here we have a titanium alloy, and we're testing it in torsion because now we want to induce this shear stress. So this is the response. This is the shear stress versus that gamma, that radian or degree that we're rotating the element through. And we want to determine G, the proportional limit, and the ultimate shear stress, and determine maximum distance at the top of the block. That the top of the block of this material can be displaced if the material behaves elastically. So what's the maximum it can kind of move if it wants to stay in the elastic region? There's a lot of things going on here, okay? So let's start first by kind of writing down this point A that we see. And that's going to be the point where we're deviating from the elastic to the plastic region. So we have this point A, and we have 0.008 for gamma, and we have 52, 52 for tau. Now we can easily find G, because we can say that's just 52 divided by 0.008, and that's 6,500 KSI. So that's first part done. Okay. Now the equation of this line OA, basically, we know that it's tau equals G gamma. We just use it to solve for that. That's Hooke's law in shear. And that means that that's just 6,500 gamma. This is Hooke's law for shear. Our proportional limit, we already solved that. That's going to be the 52 KSI because we're using the same as the yield here. So we just kind of pick that off the diagram. Now our ultimate, so I'm going to put these here. That's just the max. So let's come to the diagram. It's already showing it to you. Max tau u is 73. And our now, so we've just really right now just kind of relayed information down. There's nothing that we've done or calculated yet. Okay. So now we get to calculation. So we want to know the maximum elastic displacement and shear force. Okay, so the first thing we can do is we can look at the max elastic strain, which is at 0.008. From the diagram, right? And that's at the top of the block. So we know that gamma is in radians, and this is the angle that the block distorts. So angle is the angle that the block distorts, okay? And here, again, since we're dealing with small displacements, we can say that tangent of 0.08 is really just approximately 0.008, so I'm not going to do tangent, but then I can get the distance here that that block moves by just equaling it to d over 2, and I get this d value, and you can see that here. I'm just using this triangle. If this is gamma, opposite over adjacent, but really I'm saying this is just equal to gamma, so that's how we got this. Now, average shear stress in block. So we have our tau for yield or plastic limit, which is 52 KSI. And our tau average is equal to V over A. So we know that that's going to be the max V we can have is for the elastic region would be at 52 divided by the area, which is 3 times 4, and we get a V of 624 kips. And that's it. So we basically have used this diagram to kind of give us all of those answers and the information that we needed for this. All right, since we're almost done, I'm just going to do the last example here, and we'll just probably kind of discuss in our next class, and we can have answer any questions that come up, okay? All right, last example, we have an aluminum specimen with a given diameter and gauge length, and we're pulling with a force of 165 kilonewtons, and we elongate the gauge length to 1.2. Determine the modulus of elasticity, also determined by how much the force causes the diameter of the specimen to contract. So what's happening here is we're pulling on the bar, and as we pull, this diameter gets smaller in the middle, right? So let's start here by figuring out what we need to find, right? The first thing is we can find our average normal stress. We know we're going to have to deal with our normal stress, because this is axial deformation. That's the first thing we can really find, because we're given the 165, I'm going to put that in newtons, and we're given the area pi times 0 r squared, and we get 336.1 megapascals. And we can also get the average normal strain. It's telling us it was 1.2, and the initial length was 250. So we get 0.00480 millimeters per millimeter. Okay, the first thing now we can see, we know sigma y let me put it here, is 440. And this is less than sigma y, right? So we know that this is elastic behavior, okay? And we can get the E of aluminum now by Hooke's law. Okay, now we can use basically Poisson's ratio to get the contraction of the diameter. So let me write out the shear modulus. And we know the shear modulus is 26 because it was given right here. So we have 26 equals 70. We just calculated that. 2 over 1 plus Poisson's, and we get Poisson's ratio of 0.347. If we know that the longitudinal strain, which we just calculated, is 0.00480, and this is longitudinal because it's related to the normal stress, then we know that Poisson's ratio is equal to negative epsilon lat divided by epsilon ln. And then there we get to plug everything in. And we can solve for E lat of negative, because it's basically getting smaller. Okay, now last part here, let's get the diameter contraction. And we get this. All right, so this was the last example for topic 2. Last slide is on creep and fatigue, and I will go ahead and let you guys read over this, and then we'll briefly discuss it next class and go over any questions you guys had for this topic.